Please, a round of applause as she comes up.
Okay, please, can we pray? Our help is in the name of the Lord. Almighty and ever-living God, we thank you for the gift of life, for the gift of health, for the gift of this amazing opportunity to be together here to benefit, to gain knowledge. Father, we ask as we go about this event that we all that have left our various homes and other activities to be here will go much better than we came in the mighty name of Jesus. That at the end of today, we'll have a cause to purify
the university anthem.
University of Nigeria, in the nest. Hail and rejoice for the University boys and dreams come true. Hail and rejoice for the giants are raised. University of Nigeria, we are Marita. And rejoice for the lasting days. Diversity is exciting, let's all breeze. And rejoice for the beauty's sake. University of the glory, the pride of the land. And rejoice for the light will shine. University boys and Lord.
Put your hands together.
Amazing. You may be seated. We are celebrating innovation. We are celebrating the rise of the youth. We are celebrating invention. We are celebrating workshop. We also came to network. So find out what are their names, what do they do, where do they come from. Let's do that quickly. All right. So we're going to invite our resources who came all the way. We're going to be inviting them to go up to the high table. So first on my list, the president of Chemical Society of Nigeria, Dr. Ibeto, please, could you come up stage? Thank you, ma'am. Yes, please, ma'am. Please. Please come up stage. Put your hands together for her. You know the facility now, you know her. Don't do like you don't know.
Other principal officers present, our invited speakers and resource persons, distinguished professors and professor emeriti, distinguished scientists and participants, ladies and gentlemen of the press, lion and lionesses, great lions. With profound gratitude to the Almighty God, I'm most pleased to deliver this welcome address as the LOC chairman of the 2003 Africa appreciation to the organizing committee, interns, volunteers, and all those who have worked together tirelessly behind the scenes to make this event a success. Your dedication and hard work have ensured that everything runs smoothly, and we are deeply grateful for your contribution. Finally, I would like to conclude by extending my profound gratitude to the Royal Society of Chemistry, UK, for their unwavering support throughout AODI's endeavors. Their immense contribution and generous grants have enabled us to organize this remarkable event free of charge. This event would not have been within our reach without their invaluable support. We deeply are indebted to the Royal Society of Chemistry for their belief in our mission and dedication to fostering scientific excellence. Thank you once again for making this event a resounding success.
Come on, clap, 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 clap. Amazing. Thank you so much, sir. Thank you. Sir, please. All right. We'll take the speech from the Vice Chancellor of the University of Nigeria, Nsukka next, ably represented by Professor Igwe, the Dean of Physical Sciences, Faculty of Physical Sciences. Please put your hands together as he comes up to the podium.
Just before I read the address of the Vice Chancellor of the University, I would like, in my own capacity as the Dean of Faculty of Physical Sciences, to thank the organizers of this workshop. I'm excited about what I'm seeing today. The cream of personnel seated here at the table is exciting. For you to come all the way from UK and from every other part of the world to build capacity, it's just amazing. And I wish this had involved the entire faculty, not just chemistry. Please plan towards that. You wouldn't realize what you're doing now until you are done. The results and the outcomes of this event will reverberate for many years to come. So thank you very much. I will now go straight to read the address delivered by Professor Charles Arinze Chukwuigwe, FAS, Vice Chancellor, University of Nigeria, Nsukka, at the 2023 Africa of Our Dream Education Initiative Chemical Lecture and Workshop on Wednesday, 31st May 2023. Invited speakers and resource persons, distinguished professors and professor emeriti, distinguished scientists and participants, ladies and gentlemen, gentlemen of the press, lions and lionesses. With great pleasure, I welcome you to the 2023 Africa of Our Dream Education Initiative Chemical Science Lecture and Workshop with the theme addressing the chemical sciences gap among minority groups in Nigeria, measuring the impact of instrumentation and soft skills for global competitiveness. A lecture and workshop of this nature will undoubtedly bring together many chemical scientists from all over the country, and it will be an excellent opportunity to network with international experts. Chemical scientists in Nigeria are still trying to handle the challenges faced because of many instrumentation limitations. Indeed, Nigerian chemical scientists are among the minority as far as global chemical scientific outreach are concerned. The theme of this workshop is well thought out and timely. As you gather here with our esteemed international guests, I hope that this two-day interaction will forge a new front in global collaborations between the university staff and students and our distinguished international guests from the University of Cambridge and the University of Nottingham, as they share their expert knowledge with us on this special occasion. A 2-day lecture and workshop which promises to build capacity
greatest guy. Of the greatest awesome. I'm really excited to be back here. I started here from my undergrad. My second year got a scholarship, went back to Japan for the research program, I graduated, went back for a master's here in Japan before proceeding for my PhD at the University of Cambridge. But what I'm trying to say in summary is that wherever I am today started here. And so when we had the opportunity to run this event, versus saying that charity begins at home, I thought that's okay. Maybe it makes sense for us to launch this right here. And so without wasting more time, I'll just go straight into my address, Keynote address. We would have brought a professor or someone, higher up there to present this, but I thought that it makes sense for me to hear the story of Aodi, why the charity was set up. Not in its entirety, but at least give some scope of what we're doing. It could encourage you because tomorrow you seated here could be in a position to support other people. And so with that, I will go straight into the keynote address, which I've titled The African Dream for the Future, a focus on human capital development. So it is with great pleasure and gratitude that I stand before you today as the founder and the chairman of the board of trustees of the Africa for Dream Initiative. As we gather here today for the chemical science lecture and workshop, I am reminded of the incredible journey that has brought us together, driven by a shared vision of building a new Africa, where individuals can thrive and have access to the necessities of life. When I reflect upon the mission and goals of Aodi, it becomes clear that our path to a prosperous Africa lies in investing in health, education, opportunities, and above all, in the development of our human capital. We firmly believe empowering youth and women through education and capacity building lays the foundation for sustained prosperity and a brighter future. The establishment of Aodi in 2017 was born out of a deep sense of gratitude for a generous funding opportunities that supported my own academic journey, from my undergraduate studies to my pursuit of PhD at the University of Cambridge. Through the support and opportunities I received, including the Japan Student Service Organization Justice Scholarship, Next Scholarship, Cambridge Africa Scholarship, Cambridge Trust Scholarship, IIT Scholarship, among others. I stand before you today committed to giving back to the community that nurtured my growth. Aodi was founded as a testament to the belief that investing in products and providing access to education can transform lives and ultimately our continent. Since its inception, Aodi has been dedicated to the noble cause of youth and women empowerment. We've embarked on a multifaceted approach targeting key areas such as education and capacity building. By equipping individuals with the necessary skills and knowledge, we empower them to overcome challenges, break barriers, and realize their full potential. Aodi has made significant strides towards our vision of a thriving Africa through various programs and initiatives. Our flagship global mentorship program has provided mentorship to over 5,000 brilliant students. And we've witnessed young minds blossom through scholarships, grants, and mentorship programs. Our institutions have transformed thanks to the educational infrastructure, equipment, and sustainable livelihood initiatives Aodi has provided. Last year, through the support of Cambridge Africa Initiative, the Department of Chemistry, Engineering, Physics, and Biological Sciences at the University of Cambridge, we procure and deliver research equipment, high-performance computers, and other accessories worth over 80 million naira to the Department of Pure Industrial Chemistry and Biotech Laboratory here at the University of Nigeria. Though remarkable, these achievements are only a stepping stone to a greater tomorrow. So therefore, the chemical science lecture and workshop that brings us together is a testament to our commitment to nurturing talent and fostering knowledge exchange. By creating this platform, we aim to provide a conducive learning, collaboration, and innovation environment. This workshop catalyzes young minds to explore the fascinating world of chemical science, broadening your horizon and chart discovered frontiers. These have become necessary in the face of cutting-edge and disruptive technologies, revolutionizing how we learn and do things today. Artificial intelligence, as you know, is sweeping the globe with its power to redefine humanity. Many of us would have tested the capability of tools like ChatGPT, Google Bard, Meta AI, to mention but a few, which are already changing how we learn today. So the computational chemistry and molecular dynamics field is not left out in this cutting-edge disruption, as machine learning is already taking its form across these fields. This means that sooner or later, traditional classroom learning will be redefined in its entirety if it must produce students that have the requisite skills needed by employers today. So therefore, jobs will be displaced as a result of this. But new skills are going to be born, and only those using these new tools will compete favorably out there. New tools will be deployed to enhance learning, and you will have access to everything you need to learn and with the click of a button. However, there is still a gap between what is possible in the West and the economies like Nigeria. I've always asked myself this question: do we need to continue to play catch-up or take a leap to the future and contribute to it, just like the rest of the world? Why should it take me 3 months to synthesize a chemical compound, another 6 months to send a sample overseas for characterization, and at the end, I get a static printout that does not give me holistic characteristics of my sample? Is there no world where I can reduce the time it takes me to do all of this in an average Nigerian lab? So therefore, I hope that by the end of the 2-day workshop, you will find answers to this rhetorical question that I've posed to you. I'm not going to give the answers now. As we embark on this collective journey to build a better world, we must remain steadfast in our wisdom. We must continue to forge partnerships within Nigeria, Africa, and globally to leverage the collective power of institutions, organizations, and individuals who share our vision. Together we can create a ripple effect that transcends boundaries and inspires change. The University of Nigeria, Sudan, and other counterpart tertiary institutions around the globe have a pivotal role to play in realizing our shared aspirations and vision. Our tertiary institutions can become a stronghold of progress by championing human capital development, fostering a culture of research and innovation, and nurturing the next generation of leaders. Through the concerted and collaborative effort of institutions like UNM, Cambridge University, Nottingham, and others, alongside organizations like ours, the Africa Frontier Initiative, we can create an Africa where dreams thrive and opportunities abound. That is the African of our dream. As we strive to build a better world, we must also recognize the importance of building strong institutions that can sustain themselves, adapt to change, and wither a storm of uncertainty. Institutions that serve as the bedrock of progress and provide a solid foundation for generations to come. At Aodi, we understand the importance of building strong institutions. It is not enough to focus solely on short-term gains. We must invest in the long-term solutions that can stand the test of time. By cultivating a culture of accountability, transparency, and good governance, we can lay the groundwork for a sustainable future. Yes, we must recognize the critical importance of human capital development. Our success as a nation and continent hinges on our people's skills, knowledge, and abilities. We unlock the full potential of our human resource through investing in education, mentorship, and skills training like this one we are having today. We have a unique opportunity to champion human capital development within the university community. With its rich academic heritage and commitment to excellence, tertiary institutions like EM can play a pivotal role in shaping the future of Nigeria and Africa at large. Universities can catalyze transformative change by equipping students with the tools they need to succeed, fostering an innovative environment, and nurturing a spirit of entrepreneurship. These tools must come at the right time to be made. But the responsibility does not rest solely on the shoulders of the university. It is a collective effort that requires collaboration between academia, industry, and government. Universities must leverage the success of their alumni network to create opportunities for future students. We must forge strong partnerships that bridge the gap between theory and practice, allowing knowledge to flourish and innovation to thrive. As we look towards the future, let us keep sight of the essence of our mission. It's not just about building a better Africa. It is about building a better world. It is about creating a society where individuals like you and me are not only able to survive, but to thrive. It is about empowering the marginalized, uplifting the vulnerable, and leaving no one behind. Remember that our journey is not measured by how far we've come, but by how far we are willing to go further. Let us remain steadfast in our commitment to empire, hard work, and doing things right. Let us build strong institutions that can withstand the test of time and invest in human capital development to secure a prosperous future. Let us build capacity to drive African priorities. In conclusion, let us seize this moment to reaffirm our commitment to the cause we hold dear and remain vigilant in our pursuit of knowledge, empathy, and relentless pursuit of excellence. As we embark on this transformative journey, may we continue to strive for greatness, uplift one another, and build a new Africa where everyone can realize their dreams. This workshop will be a catalyst for transformative change in global academic endeavors. Together, let's build a future we can all be proud of. Remember that the road to progress is paved with empathy, hard work, and steadfast commitment to doing things right. Thank you, and I wish you all a prosperous and enlightened chemical science lecture and launch.
Thank you so much. Those were touching words. It's all about giving back. It's all about giving back. I have a brief announcement. Please, everyone is encouraged to wear their tags. No matter what you're doing, no matter where you are in this vicinity, please wear your tags. Even during the break, please wear your tags. It's very important. We will call on the head of the Department of Care and Industrial Chemistry who walked in while the keynote address was going on. for his opening remarks. Please put your hands together for Professor Ejike Morris.
Thank you very much, good day, ladies and gentlemen. Some exigencies of office, especially now that the university is involved in one of the major assignments that has to do with welfare of staff, which we don't take very lightly at this time. The university, for other reasons, we also why the dean of the faculty that represented the representative of vice chancellor had to give our ability to permit me to present this very short welcome message by the Department of Pure and Information Chemistry, University of Nigeria, headed by myself during this degree article of our junior chemical lecture and workshop today. This is it's not a happenstance that we are all coming together today and tomorrow to participate in a lecture and workshop being hosted by Aodi and the Department of Chemistry of the University of Nigeria. Having the team addressing the chemical sciences gap among minorities in Nigeria, measure the impact of instrumentation and soft skills for global competitiveness. It's the timely event, considering the fact that the need to address the gap between research standards in Nigeria and what is obtainable globally has become very pertinent. This event is coming at the tail end of my holiday tenure as the head of government plan in our university. In the past, 1 year, my Aodi as a school has made solutions of something about equipment, tools, desktop computers, was being to accept on behalf of the department, the organization and those things of this individuals and all important events. And lastly, appointed Professor John we as a lawyer, as the LOC chairman for this event. Coincidentally, Professor John was a mentor, an excellent of Dr. Izor. I welcome and urge all of us to participate fully in this program, which from all invitations is going to be a fulfilling as it will be rewarded. Where in the words of Dr. Izor, theory will meet practice. Thank you and God bless.
Please put your hands together. We are almost at the appointed time. For in 2 minutes, I want 2 students, a male and a female, to please come up and tell us what are your expectations for today's training. 2 persons, volunteers. Oh yeah, now you are lions and lionesses. You can't be sitting down when they say volunteer to come and talk. You should be standing up, like I should have several persons standing up. Volunteer, okay. Let me do my peeking then. And you know those is called to survive. All right, so you tell us your name and tell us your expectations.
Okay, all with this one. Today, I was going to present results. I came here to get inspired and to learn more about my course and its applications and stuff. So basically, I'm just hoping to learn results from today. Thank you.
Put your hands together for him. He has gone through a lot to come and learn a lot. All right, ma'am. Please, could you tell us your name and what it is?
Good morning, everyone. I am Assistant Director, and I expect to have an inspiring lecture today and meet excellent people today. Thank you.
Thank you very much. That's very important, the meeting of excellent people, because it's a gathering of excellent people. So we're going straight to the first part of the workshop, and we are going to be introducing our speaker. He is the Deputy Head of Department at the Yusuf Ahmed Department of Chemistry at the University of Cambridge, and has held a number of senior roles across the collegiate university. His research interests have focused on supramolecular chemistry, molecular recognition, and spectroscopic characterization of complex chemical systems. In addition to his research and administrative responsibilities, Nick has considerable experience in teaching, outreach, mentoring, and developing inclusive working cultures for students and staff. Ladies and gentlemen, please stand to your feet and with a clap ovation, let's welcome Dr. Nick Campos. Please give him a lion and lionesses welcome.
Okay, please sit down, relax. We are a little behind time, so what I'm going to try and do is I'm going to try and be very efficient. We may lose a session or two, but the thing that you need to know is that the slides for what I was going to present all day are available to you as a PDF. I think the team will get it to you. If I need to make any updates, I'll do that at the end of the day and provide you so that you have a resource that you can tap into whenever you want. I'm also you're going to see a lot of me today, so my apologies for taking up so much of your time. I'm also going to see you tomorrow afternoon where I'll give you my reflections on career and mentoring, because in a strange way, I've known David and the reason we're here is because we believe in what David is doing, and we believe in all the African students we met in Cambridge over the years, and it is our view that it was very much worth the effort to come here, to meet with you, to talk to you, and like collaborators to exchange ideas. So I hope that we fulfill the objective of giving you some idea of the knowledge base that we have access to. So sit back and genuinely enjoy. I don't know if you can see the PowerPoint presentations from everywhere. I am a chemist by background. I am Australian. My parents are Greek migrants. After the war, they were quite poor, so they moved to Australia. I grew up and was educated there, and I went to Cambridge, where I had a fantastic time. I've met lots of wonderful people, like Alex Tom, who is going to talk to you tomorrow, who I knew as an 18-year-old when he first came to Cambridge and saw his career flourish. And then David, who did his PhD with Alex, I met and was inspired by, and has gone on to great things. And we'll talk more about what he's doing tomorrow. But because we're a bit behind time, I'm just going to go straight to the science. Because we are scientists, and what we want to do is exchange ideas. Because all we need to do is not provide the answers to all the problems, but try to unpack in sort of 40-minute sessions what we try to do in 6 or 12 hours lectures hanging. And I don't have any problem doing this because having met David and a couple of African and Nigerian students who mentored to come to Cambridge, I've known years of that intellectual abilities. You can do this. So all I want to do is sensitize you to the technique and the key things you need to know in order to do really good science. All of the computation stuff, really, science is about creating data. And data is about experimental information. So, you might have to do the slides for me backwards and forwards because I can't do it from here. This is what the radio frequency you might teach from here. Okay. Was that you or was that a fish? I'm thinking, was it you? I'll come to the front. It'll make a difference. So I'm going to do this from here, and I'm not going to try and trip. If I trip, someone just pick me up and bring me back on the stage. So I'm sorry I'm getting in the way. I really want to be here. Okay. So, why are we interested in adapting analytical chemistry? And the answer is simple. We spend most of our time as scientists, as chemists, designing experiments, whether it's drug molecules, new materials, or next generation vacuum. We then make the compound. That takes a lot of effort. But ultimately, we need to analyze it, because until we analyze it, we don't know if we made it. Of course, if the spectroscopic technique tells you you made what you plan to make, that's good news. You go and have a cup of tea and congratulate yourself on success. But that's not always the case. The problem is that the analysis tells you that you did not make the compound that you wanted to make. Now that in itself is not a crisis. Because if you've got the analytical technique, even if you've not made what you wanted to make, things like NMR, IR, UV will give you a hint about what you unexpectedly made, which may be an important outcome. And if you know why you didn't make the thing that you did, you can go back and redesign the experiment again. So it's just this little feedback loop where you go back and do the experiment all over again. Now, what you've got to think about is what technique are you going to use? And as a scientist, you sit there in the lab and think, okay, I've got access to equipment, I'm going to send something away to the laboratory. What technique are we going to use? And here you've got to think, you cannot see this clearly, but hopefully you can see it on the note. What we're looking at is time frames. So what we have here is a time frame and a wavelength frame, and what we see here is a type of from sponges. So a lot of things we extract from nature, from tree bark or from things in the ocean. And that is a complicated molecule. It's complicated because it's got a lot of stereocenters, for those of you who've done organic chemistry, and it's very hard to synthesize. It's been synthesized by about a dozen research groups around the world over the last 30 or so years. 2 in my own department. It most probably, to develop the synthesis of this, may have taken half a dozen PhDs worth of work to synthesize it. It's hard because you've got to build it every bit at a time. But once you get the synthesis right, imagine if you can make something with potent antibacterial properties, how important it is. And of course, if we're really going to look at the future of chemistry, my colleagues tomorrow will tell you it's AI and code. As an experimentalist, I'd say it's biology. And you're really looking at complex molecules like protein. And there's hemoglobin, that's the protein in your blood that makes your blood red. All biological molecules are colorless if they're made from carbon and hydrogen, which most molecules and most proteins are. This one is highly colored because it has 4 of these porphyrin molecules I showed you a moment ago, which are these disc-like molecules that bind iron. Iron binds oxygen. Oxygen, when it binds iron, when it becomes oxidized, becomes red. And that's what gives blood its color. And you can characterize these by NMR. But by golly, that's really, really hard to do. Right? The way that this structure was solved is by X-ray crystallography. This was done by Max Perutz in Cambridge. The same year he won the Nobel Prize, Crick and Watson won the Nobel Prize for discovering the structure of DNA. A good year for chemical biology. Okay. So, other thing you need to keep in mind is that if your compound is valuable, sometimes in the analysis, you're not going to get it back. So whether you do the analysis or you've sent it somewhere away, you may not get it back. And if you've got small quantities, be very careful about which technique you use. So if we look at something like UV visible spectrometry or spectroscopy, there you need small quantities, 2 to 5 milligrams. You dissolve it. I'll show you in a moment what a spectrometer looks like and what to be wary about when you approach this technique. You dissolve small quantities, you run your spectrum, you get it back, you extract it, and evaporate the salt, you get your compound back. And that's good news for me when you make a compound that takes years and years to make. If you do IR, you usually crush your sample in New-Gel Mull, you put it in a machine, you're not likely going to get it back. But the good thing is you don't need large quantities. You need just enough to get into a little pestle, grind it, get it, spec it, and so on. NMR, 5 to 25 milligrams. It is the most used spectroscopic technique. In chemistry department in Cambridge, we have 20 spectrometers that are running 24/7 every day of the year. Right? This is the technique of choice. You're using anywhere between 5 and 25 milligrams, depending on the size of the molecule. You get all your compound back. You dissolve it, you run it, you get it back, you recover all of it. If you're doing mass spectrometry, which I'll talk about, you need tiny quantities, but you don't get it back. Because mass spectrometry requires you to super excite your molecules so that it usually breaks up into lots and lots of bits, you never get it back. And X-ray crystallography, XRD, well, you use as much as you can because you've got to grow a crystal. And that is almost a sort of an unknown process. If you can grow a perfect crystal, X-ray is great. If you can't, and usually you can't, it's not a great technique. But usually you don't get back the material because after you bombard it with X-rays, it starts to decompose and it will oxidize, so you may not get it back. So keep in mind which technique is appropriate for the sort of compounds that you have. Now, things to keep in mind if you're not doing, and I'll show you some single molecule techniques in a moment. When you're analyzing your NMR tube or your little vial for UV visible spectroscopy, remember, you're not really measuring a single molecule. For all of these techniques, you're looking at the average of the billions of molecules that are floating in your solution. That's important. You're looking at an ensemble average of the effect of your compound in the medium in which you have it at the time that you run a spectrum. This means there may be other things in there. And there may be things that the technique you're using cannot see. So, for example, if you're running proton NMR, or carbon NMR, you're only looking at hydrogens or carbons. So if you've got something that's rich in nitrogen, or you've got some inorganic salts as contaminants, you simply will not see them because they're invisible to the technique. Which is why when you make a compound, a test of its purity, typically for journals, is to do a combustion elemental analysis technique, because that defines how many different types of atoms and how many you have in the compound. Very often in the lab, one of the students will come and present a really nice spectrum and say, I've made the compound. Great enthusiasm. Looks fantastic. And you say, right, you put a lot into the machine and it looks like a lot in there. I say, but I've made what I wanted. And you say, go and use one of the other techniques to find out if there's anything else in there. And often they find that over half of the compound they put in is not what they expected, but some inorganic impurity that just didn't give signals according to that technique. So keep that in mind. That's important. So you think you may be running your little beaker's just got only the compounds that you're interested in, but you're going to have a lot of other impurities, maybe bits from your starting chemistry, maybe a lot of inorganic impurities. They could be isomers of your compound, they could be contaminants. Typically, it's the inorganic salts in standard chemical synthesis that sometimes it's there, but we just don't see it. So that's our view of how instrumentation works. Now, taking into account lunch, all I want to do is I'm powering through sort of 2 of the sessions very quickly. Now, I'm around all day, right? I will see you. You ask anything about it. The whole point of us coming here in person, not doing this online, is we're bored of doing things online, right? Nothing nicer than coming and meeting people in person, but it means that you can come and find us between the sessions after tomorrow morning and come and specifically ask questions about a technique that matters to you. So I'm going to go through this relatively quickly, simply to let you know, you must really be aware of some of these techniques. Maybe you're not. And if you're not, it's good for you to maybe see something that is state of the art and which may be defining the way that we do chemical analysis in the next 10 or 20 years. So what's the future look like? Future is mostly material chemistry, and it's about engineering compounds in very particular ways. We do call it molecular design, molecular architecture, material science, and so on. This matters for energy, next generation battery storage. Professor Claire Gray in my department is one of the world experts in battery design. She's got about 40 people that work with her. She has a number of collaborators in Africa, right, that she works with, because the view is energy matters to all of us. So there's no point just doing something in Cambridge or Nottingham or sort of Harvard. We've got to do it everywhere, which is why we like. At least the slide is working. So it'll come back on in a minute. Can you hear me at the back if I speak relatively loudly? Excellent. Right. Frees up my hand, which is better. Okay, so it's about doing chemical, it's material engineering. So here's an example of an iron platinum nanostructure. So these are nanoparticles that are constructed by bringing iron and platinum atoms together in a defined stoichiometry. And to make nanoparticles, usually you have to surround them by an appropriate surfactant. So this is work that a colleague in my department, Andrew Wheatley, does. I've got the ODIs at the bottom, so from the PDFs you put that online and you'll be able to see the journal, you'll be able to see the article. But when you make these, you can't do NMR, UV, IR, mass spectrometry, because you don't want to break up the thing that you've made. So the way they analyze these is using electron microscopy. Now this is an expensive and very delicate technique. The machines cost a lot of money, and they require specialist technicians to make sure that the instruments work and that you tune them so that you get the right stuff out. Because I guess instrumentation is a bit like a sports car. Only some people can make sports cars go fast, right? I'm a terrible driver, so if I had a fancy sports car, I would mostly try not to drive it, especially here. Last night the trip here was quite a challenge. So what we're doing here is we're using electron microscopy. So you make your particles, you sit them on gold wafers, and then you bombard them with beams of electrons. You're going to do this either by seeing the electrons go through the particle, Here's another example, one of my colleagues, Silvia Vitalini, who's working on materials. The shape of which, as it changes color. After all, plants by growing crystallites in a particular type of orientation, they interact with light in a way which changes their color. So the key is interested in when you different types of light to see how they interact. This is crazy stuff. Like science. But when it works well, what you're doing, you can engineer really, really nice chemistry. Another of my colleagues, Jen Zhang, is interested in learning from biology how to make things like microfibers. Here's an example of using a 3D printer. So this is a commercial, high standard 3D printer where she embeds the appropriate molecule and the glue component, and she literally makes little pins. Lots and lots of them that you can't see by eye. You need electron microscopy to look at them. And here's an electron micrograph which shows what look like little pins that are just sitting on a surface. Now, if you do this, of course, the surface area of the compound is enormous. And it makes brilliant catalysis. But the other thing you do is little things like, geckos. And how geckos can sort of walk up glass and they can walk across a ceiling, right? They defy gravity. And they defy gravity because on their little paws, they've essentially got very, very, very long, spangly sort of assemblies that when they press against glass, it creates suction because they have very, very high surface, energy, very high surface area, and they get animated. Here's an example. Now we've lost the slide. This is going to be hard to do. So at least as you saw the slide. There, I will try and explain the technique that if you imagine that you've got a forest of trees, you're either going to look at a technique where you try and look at one tree at a time, but that doesn't give you information about the ecosystem of the whole forest. This is where electron microscopy allows you to scan across the material to different magnifications so you can see how far apart the trees are, how tall they are, and whether they're interacting with each other. And I'm sure that convinces you that if you're trying to engineer something to that level of detail, you need to be able to characterize it. So really the future is about looking at things using electron microscopy. So I'm going to do one more slide on electron microscopy. We have a number of my colleagues in the department who are working in chemical biology in the area of solving the problem of Alzheimer's disease. So Alzheimer's, which as I get older, I realize is likely to affect me. Every time I see them in the lab, I say, have you solved the problem yet? Because as I get older, this is going to affect me. So I solve the problem quickly. Two of them are much older than me, and they say they've got a vested interest in solving the problem first. But let's see how they go. Those of you who are aware of this know that what we think is happening with Alzheimer's is that proteins, amyloids, start to cluster together to form a precipitate in the brain that creates these platelets which are quite hard. And this affects the morphology of the brain. The brain is not soft as you'd expect it, but it becomes spongy with little holes and a break in the spaces which affect the neurons, the memory, and so on. And what they do is they create these fibrils in the lab and they image them using electron microscopy because, like good scientists, if you know how to fold them and you can start to work how to unfold them or stop them folding in the first place, you have made scientific progress. And there are some nice images there showing these little fibrils that they've created using electron microscopy. The last thing that I was going to show is something that I did back in, I was shocked myself when I looked at this the other day, back in 1999, that may be before some of you were even born. And here we used scanning tunneling microscopy to image single molecules that have been allowed to sit on a surface. Maybe one of the presentations that I'll just bring it up to show you was quite exciting at the time, because in terms of instrumentation, scanning tunneling microscopy won the Nobel Prize for Physics in the 80s. And at the time, if you wanted to use this technique, you had to make the machine yourself. And we had colleagues in engineering who built this incredible machine in an enormous room, right? It worked one day in 14 because something would always break down. And now you can buy these commercially. And you can use STM or AFM to image single molecules. And what we have made is we've made these forefronts, these circular molecules, which are in E. We've made 2 of these forefronts, and we've bound them so they form a little shape like this. Forefront here, forefront here. And in solution, what they can do is they're doing this. We want to do what happens if we took them out of solution, where they don't have the ability to be mobile, and see what they do if they sit on a surface. And if you evaporate them at the right range, and you do the experiment carefully, you can make some of these evaporate from the solid state. It's a beautiful red powder. They evaporate, they move through a machine, and then they collapse on a copper surface. And what we saw by STM, that they sat either like that, or they sat like this. So we could image 2 different forms of the same molecule. And for the sort of catalysis that we wanted to do, of course, we wanted more of this and less of this, but we were able to image these not as an NMR, mass material, but single, discrete molecules on the surface. And that was very exciting. Okay, so that's sort of where I wanted to say, this is where instrumentation is, this is the considerations you have when you do an experiment, the things you need to keep in the back of your mind when you're thinking about what technique you're going to use. It's most really around convenient time for lunch anyway. So what we'll do is, I don't know what David will be organised, how you want to do this. I mean, because we've lost about 2 sessions, and I don't want to go through some of the other sessions so far today, completely meaningless. When we get back after lunch, what we'll do is I'll decide what order to do them in to sort of maximize the exposure. And since you've got the PDFs, if there's anything on the slide that's particularly interesting or that you want to know more about, come and find me and I'll give you all the information I can. Okay, so it made it a little bit interesting doing the presentation with no PowerPoint. So I'm hoping, but I think we just did enough as scientists. We've gotten to the point where I could almost describe the techniques just using my hands. Great. Okay. So I suppose have a lunch break. Back. I think the lunch break was scheduled to be 12 to 1. So I will see. I'm back at 1 or maybe 5 or 10 to 1. David, I can't see David or Chisholm. Anyone in the crowd? David. Through. What do for lunch?
I think we can break for lunch.
And what time? Come back at 1 or 2:30? Okay, all right, so go and enjoy lunch. Hopefully we'll see you. And remember, Alex and Bang are here as well. You met them at the beginning. We'll try and go around and mix and meet you. Please come and talk to us about anything we can help with, but go and have lunch and we'll get back here for a 1 o'clock start. I'm pretty sharp, so we don't lose any more time. Great. Okay, see you in about 55 minutes. Okay.
Thank you, sir. Thank you. All right. Now, please, let's listen up. We'll have a break, not yet lunch, but we'll just have a break. So please sit where you are. They will come serve you, and when they serve you, you can now move around a bit. This will just be like for 10 minutes, 15 minutes later. Please sit where you are. Stay where you are till they give you what you use for your break. Then you can get up and move around. So we don't have issues with people moving up and down. Thank you.
sample into a machine and then sitting back and watching the machine do its magic. So here we're trying to look at how spectroscopic techniques work. Now, the ones that are most relevant, I think it's fair to say that are the most regularly used techniques, and the ones that please ask me more about today or tomorrow, is ultraviolet UV visible. And that's important because the cheapest spectroscopy that we can use is what we see. And if you're doing compounds where they change color, for example, in organic chemistry in particular, and I'll explain why in a moment, if you take a metal complex and it's purple and you change one of the ligands and it turns green, you know you've done something. But that happens only if you see something in the visible region, which is what our eyes have got the receptors for. This is used a lot. Relatively cheap technique. We'll talk about this in a moment. You know, it's accessible. A lot of labs have it. IR spectroscopy also very useful because now we're going to see we're not looking at how electrons are absorbed, but how bonds in molecules stretch. Different type of technique under the underlying theory. There's also mass spectrometry. I mentioned that in mass spectrometry, what you do is you take your molecule, you super excite it so that bonds start to fragment, and then like a thinking person's Lego, you start to look at the size of the chunks to determine what your compound was. And the one that's used much more than most, I think, is NMR, nuclear magnetic resonance spectroscopy. Very versatile, very popular, very good because it analyzes pretty much everything in solution. But if you can get something in a crystal, if you can get a pure crystal, you use single crystal X-ray diffraction. The key here, remember, is I said it's got to be a single crystal. And that means that we can all make solids, but the crystal you use in XRD has to be a pure crystal without flaws, and with all the molecules have assembled in a compact and efficient way. Now, how do these work? Fundamentally, all spectroscopy requires you taking the sample of the compound that you've made and you do something to perturb it or to excite it. I mean, I've shown a little bell here that if you're telling your molecule, do something, whether you do it with electromagnetic radiation or whether you do it by magnetic spins, you perturb the molecules and then you listen to what happens at the end. That's spectroscopy in a nutshell. And that spectroscopy you can show to your friends who do law or literature that they can understand, right? What do we do as scientists? We make molecules, we then take them, we excite them, and we listen to what they do by virtue of that interaction. That is what spectroscopy is about, in the simplest sense. Now, all the other schematics are just going to be variants of this sort of this sort of methodology. So here we have UV visible spectroscopy, color. So what we do here, these machines have been around for a long time, and the underlying science hasn't changed. What surprised me last week when I went to take a photograph of a modern machine is how small and compact they've become. But that's all to do with chips and detectors. So what you do is you take your sample, there's a sample here, and you irradiate it with light. And what happens is light goes in, light is split on two mirrors. One path goes through the sample, one path goes through a vial that does not contain the sample. That's called the blank. So if what I've done with the sample is if I've got my sample in a little plastic cuvette and I've made it in chloroform, then what I want to do is put a little plastic cuvette with chloroform, but not compound, in parallel. And what the machine does is the light goes through the two together. The machine then subtracts the reference from the sample and you get a spectrum. And that's how UV spectroscopy works. Light goes through the sample, and if it doesn't do anything, light comes out the other end. But at some wavelengths, it goes into the sample and it absorbs light because electrons jump. We'll see that in a moment. That's what UV spectroscopy does. That's what a modern UV spectrometer looks like. I was surprised. What I was expecting is this. This is what I did when I was young. These things sit on a bench. They're about this big. They're about this big with a computer on the side. Apparently, when I went to the technician, I said, I'm going to go and speak to some chemistry colleagues in Africa, and I wanted to sort of show some instruments. He said, you want the modern ones or the old ones? I said, I'll look at both. And the modern one was this. This is this big. And they cost about £10,000. That's relatively cheap. And you can go, I noticed, online or eBay and get them even cheaper from someone, right? And they sit on a bench and they're robust. They don't break down. You can run sample after sample after sample. These are great. But we'll see in a moment when I talk about UV visible spectroscopy in more detail with AR a little bit later in the afternoon, you get some really, really useful information out of this technique. Now, IR spectroscopy is a process where you excite your molecule by stretching the bonds. So you're hitting it with light in the infrared region. And the technique is no different to UV. You're doing fundamentally the same thing. You've got your sample, you've got your reference, you're passing IR light now. You've gone to a different wavelength or frequency region. And then on the other side, there's a little clever mirror that sort of does the splitting. And then what you do is you get the spectrum out the other end. UV visible, as you'll see in a moment, usually, if at all, will have an absorption for a chromophore in the molecule. You'll see what I mean about that a little bit later. IR has lots of absorptions because molecules are made up of lots of different types of bonds, and they all stretch at different frequencies. So you don't get just one type of absorption, you get lots and lots of different absorptions. And as you'll see in a moment when I show you an IR spectrum, we don't try to analyze every line in an IR spectrum. Some of them are there because that's the personality of our molecule. We're looking at the ones which tell us something very specific. And what I've said to colleagues and undergraduates when we talk about IR is like trying to determine the defining characteristic of a person. What you don't want to do is go and measure the length between their shoulder and the elbow and the ankle. You're looking for diagnostic things. Length of hair, color of hair, height. These are diagnostic features, and this is what IR helps us work out. IR spectrometers are pretty compact. Again, not very expensive. These are just sitting in the graduate laboratories. Right? You get these in boxes. You can carry them around. You take your compound. Remember, we said about 5 milligrams. You grind it up, usually in a gel. You put a drop. It doesn't come up well. There's a little plate just there. So you put a little drop. You move the detector on top of the little hole. You press it, and then the light goes through your sample, and then you get a spectrum on the computer that comes out the other end quite easily. Mass spectrometry. When I started my PhD, no one was interested in mass spectrometry because people thought, well, it's all been done. There's nothing else to do. And it was all done by ionization. In the last 10 years or 15 years, it's become a hot technique. Because now it's, again, technology, detectors, chip, vacuum chambers, and so on. And these could be very expensive. One of my colleagues in our mass spec section is very keen. He said, oh, this is a fantastic piece of equipment. We want it. Nick, we really want it. I said, let's buy it. How much does it cost? He said, about £1 million. I said, we're not going to buy it. Right? $1 million is a lot of money. Right? But you can use other techniques which do the fragmentation a slightly more brutal way, but you get nice results. But the underlying theory is exactly the same. So the schematic is a little more complicated. And what you have on one side is you take your sample, this is the green blob, you put in a chamber, and then you put the whole system under very high vacuum. This can be expensive because if the vacuum goes or if you lose power during the run, it just sucks back air and you can just burn your detectors. This is the bit that's the expensive and the bit that can go wrong. The rest of the machine is pretty robust. So you take your sample, you put under vacuum, and then with a filament, you heat it really hot. Or you bombard it with beams of electrons. Now your little molecule is sitting there very happily being what it is, and all of a sudden you hit it with a lot of energy, and it starts to get very excited. And as you'll see in a moment, as it gets excited, some bits break off. And as they break off, it fragments. The bits that are not positively charged, this is the key bit, they're not positively charged. Any fragment that does not carry a positive charge gets sucked out into the vacuum pump. Because what we've done down here is we've put a big positive charge a positive charge here. The other half of my plus does not appear. I will make sure you can see it in the PDF. You put a big positive charge here, so anything that's positive sees the positive charge that it says, I'm repelling. Plus and plus repel. So as they repel, they push very hard and they fly off into the chamber. As they fly off into the chamber, we've got different types of electromagnets and permanent magnets which act as lenses to determine what happens to the fragment. And as the bits fragment, they fly across the instrument, and depending on their weight or their mass, depending on how big the fragments are, they fly across the chamber and they land in the detector, which is a big detector plate here. This, of course, is going to be negatively charged, so that the plus things we form are going like this across the chamber. Now, I'm going to try, I need my hands, because I can't do this with just my feet, so I'm going to put the microphone down in a moment. But what I'm going to do is I'm going to fragment into 3 bits. My head and my 2 hands are going to fall apart. And imagine what happens in the mass spectrometer as I move from this side to this side. Okay? Now, when I get excited and I break up, it's going to hurt. Okay? So imagine that you have a bucket with fragments, and you take your bucket and you throw it. Some bits are going to fall faster than other things. And that's what the mass spectrometer is detecting. Now, it won't surprise you that because my 3 bits needed to sort of stretch, the longer the spectrometer is, the greater the curvature, the better the spreading at the detector at the end. You may say, that's a clever idea. How long can you make the detector? If it's good, if it's 1 meter, if you make the path 5 meters, it will be better still, because you give the components more time to come apart. Problem: 5 meters is a lot to fit into a lab. More metal, more electronics, more chance for things to break down. Also, you're not sure that along the way you won't get imperfections in the sort of magnetic lenses, so things can sort of muck up, they can go wrong. Also, what you want to do is clever things. If you think of me fragmenting, what you want to do is my 3 bits as I fragment, you want to take my fragment that's my left hand, isolate it, and hit it again so that it fragments into its own little pieces. And you want to take one of those pieces and fragment this again and see what happens when it comes out the other end. So you're doing multiple fragmentations. Then you need something which is going to be 10 or 15 meters long, and that's just not practical. So the clever thing they do is they just zigzag it. You just make your thing shorter by, rather than wanting a single long path, you coil the path. So rather than being 5 meters like this, it does 5 meters like this. And it goes down. So that's the techniques that do the really clever stuff these days. So what they look like now is, sorry, yeah, that's a terrible in the light image, but that's a QTOF mass spectrometer, which is sort of like a fancy HPLC for those of you that think about HPLC. You put your molecule in, you do this sort of fragmentation, some very clever magnets, and then you look at the bits. This machine is very good for small biological molecules. The top, as you can see, there's just a standard screen. The box next to it is about this big. Very easy, not very expensive. But then you've got other pieces of equipment like this. This is sort of a fancy sort of quadrupole system, which has got lots and lots of lenses. This is a very big table. It's much longer. When I went to measure it the other day when I took the picture, it's longer than my hand stretch. It's a big piece of equipment, and it's delicate. It's used mostly for biological systems. And then NMR. This is the thing I spent most of my career working on. It's a powerful technique. It's very forgiving. It's very robust. If you train students on this, in about half an hour, they could quickly run a sample. If you want to do fancy stuff, it does take longer. To process spectra, and I won't have a chance today to sort of go through a processing session, but listen, you're young and bright, right? You're more tech savvy than I am. Any software you buy, a lot of it you can get academically online. So TopSpin is the popular system that's generated by Brooker. It used to be very expensive to buy. I was told that as long as you buy it through an academic address, your university address, you can download it for free. Mestranova is another popular one that you can get a basic set free online. They are pretty easy to work on. They are button, they are sort of icon driven. You can manipulate your spectra, you can get really, really good data out of them. But NMR is what we run 95% of the time in the department. And this is slightly different to what we saw before, because here you're not doing electronic excitations. Here you're doing magnetic dipole excitations. So this is looking at what happens to the nucleus of the atoms, which you can represent as a dipole, when you hit them with a radio frequency pulse and they go between a higher and a lower energy state. It's a fair bit of theory there. I don't want to go into it because most practical synthetic chemists are not interested. But if you're interested in the theory of NMR, you can get great stuff online. My colleague James Keeler has written the best book on NMR, on the theory of NMR, including the sort of quantum mechanics that I don't understand, but Bang and Alex do, right? And also online, he has 6 lectures, I think from a course he gave in Australia. James Keeler, NMR lectures on Google. They are the best lectures of the type that are given anywhere. And they accompany the book. So it's James Keeler, NMR lectures on Google, and you'll find them. And there it describes the theory. James is not interested in what the spectrum looks like. We always have this funny thing where he comes and says, what does this spectrum mean? I said, you're the theory expert. He said, oh, I know how to do the quantum mechanics. I'm not interested. I don't understand how to characterize these things. Which is why I'm going to move away from the quantum mechanics and say, all you need to know is you make your sample, you dissolve it in an appropriate solvent, usually chloroform, you put it in a magnet. The magnetic field from north to south means that the magnetic dipoles align. Then what you do with a radio frequency generator, that's the radio frequency transmitter, it's a bit like a radio station frequency, which is why sometimes these rooms have to be put in the basement in copper-lined rooms just to sort of protect stray radio frequency pulses from your local pop station, right, interfering with your experiment. And once you hit this with a radio frequency pulse, you then listen to what the nuclei do as they go back to relaxation. And we listen through a little coil that's wrapped around the sample. The computer does all the work and you get an NMR spectrum at the end. And I'll show you quite a lot of NMR spectra when we do NMR in a little bit more detail in a moment. NMR spectrometers typically look like this. You may have seen pictures. Now you can buy NMR spectrometers that sit on a bench top. They're tiny, they're not very sensitive, they're surprisingly cheap. Industrial chemists like them because if all you really want to know is if you got A or B in your sample, these machines do it. But the machines that we have, because they're for research purposes, this is a 500 megahertz spectrometer, and it's about 200, 250,000 pounds. Not cheap, but it's very, very, very useful. And they go from about 180, 100,000 to close to 1 million, depending on how big the magnet is. The thing that costs is a magnet. And the magnet is just a giant electromagnet. You take a wire and you wrap it around the toilet roll and you pass a current, you generate an electromagnet. And if you take a coil and then you pass a magnet through the coil, you generate a current. Basic physics. This is a very expensive magnet which is kept at liquid helium temperature. So our coil, there is a port at the top where you fill it with liquid helium and then fill it with liquid nitrogen. And the coil now is superconducting. That's the expensive. The physics is quite easy. You put the sample. So yeah, and this is going to be hard with my hands. So you put the sample in the top, you irradiate it, it collects information, it goes to a box where it has a radio frequency transmitters, and then it just comes up on a computer. If we were able to cut one of these things down the middle, these expensive magnets are nothing more than a 25-pound piece of wire. So all the So I'll just give it a second for the team to, yep, it's on. So NMR is a technique that we use a lot. And I think that's something that you're likely to ask me questions about. And from talking to David, it seems that, and I think the reference at the beginning is that very often that's what you do. And I think that's what David has found frustrating over the years, that you're doing the clever science, you're making the compounds, and you've got to post your compound somewhere else so someone can run the spectrum and then send you back a printout which may not have the information that you actually want. What we wanted to do if we had a chance, and we'll see how we go this time, but I thought it'd be nice maybe just to show you how to process a spectrum to say, well, if this is what I got, I can't get the information I want. I want to look at a multiple, how you expand it. But again, all of those resources are available online. So the last technique, keeping an eye on time, was just going to be single crystal X-ray crystallography. And this is a technique, again, like most things, even though we don't want to admit it, physicists, our colleagues in physics pretty much crack the problems early on. NMR, UV, X-ray, it all starts in physics. And actually, X-ray crystallography has a very proud Cambridge tradition because it was the Thomsons. There are generations of physicists in the sort of early part of the sort of late 19th and early 20th century that discovered the electron, discovered the proton, came up with the techniques which characterize these things. The detector will just come on in a moment. An X-ray is really quite simple. It's actually quite ingenious. You take your perfect crystal, where all the atoms are compacted uniformly and perfectly. So there's a long-range order in 3 dimensions. You hit them with a beam of X-ray radiation. That has a lot of power, right? And what a generation of scientists found is that if you pass a beam through a crystal, as the beam hits not the electrons, but the nuclei of the atoms, the electrons beam diffracts. And if you do this by going around the crystal and doing this lots and lots and lots and lots of different times, what you detect is an electron density map. And the electron density map allows you to determine in 3 dimensions what the molecule looks like. So let us be clear. Apart from the fancy electron microscopy that I showed you a little bit earlier, which is a very recent development, this was the only way where we could definitively say to colleagues in the chemical community, I have made the molecule, and this is exactly what it looks like. Bond lengths, bond angles, interaction between molecules, if you've got intermolecular interactions, hydrogen bonds, and so on. Really, really powerful technique. And this is a hard slog. So Dorothy Hodgkin, a phenomenally clever scientist who in Oxford, Cambridge undergraduate, I think, or PhD, so she had a great start in life, and then went across to the other great university in England, Oxford, and spent a career trying to use X-ray to look at biological structures. And this is really hard work because you're generating hours and days of data, and then you're manipulating and calculating and doing a lot of complicated calculations. And she was able to map in 3 dimensions the shapes of molecules like penicillin, proteins. Extraordinary work. A phenomenally clever woman who dedicated a lot of time and patience, and it took patience, months and months of data, of drawing little trigonometric equations to work out how the X-ray beam spread out. Fantastic technique. Now you've got particle accelerators, like you go to CERN, in Switzerland, a huge particle accelerator, and the power of the X-rays that you get there are such that you get phenomenal resolution and tiny crystals. Because in the sort of spectrometer that I'm going to show you here, the one that's in the department in chemistry, these are now pretty routine. Your crystal has to be relatively large, at least about 0.5 millimeter by 0.5 millimeter by 0.5 millimeter. And sometimes if you don't have enough material, you don't have enough to make a crystal that big. The crystals that you get are tiny. You have to look at them under a microscope. If you can take them to a high energy source like CERN, under a microscope, you can pick one up at the top of at the tip of a needle, set it in gel, and then do it on a high energy source and get phenomenal structures, usually basically protein and protein type interactions. Really, really fantastic science. Let me just... So there it is. So again, sorry, because of the light, it doesn't come off here. So we have a liquid nitrogen tank, because usually you want to cool your crystal while you're doing this experiment. You're trying to minimize molecular vibrations in your crystal. Because if something's vibrating, the X-ray experiment sees it wobble. So you cool the crystal, just blow cold air on the crystal, and it all happens in here. And I sort of took a close-up shot. And what you see is the guts of the instrument. A bit of a delay, and just follow my red dot. There's a little plastic capillary on that line here, and at the end you stick the crystal, and then there's a beam which generates the X-ray, and as the X-ray goes through the crystal, it diffracts in 3 dimensions, and it's picked up by this big glass detector. So it's a sort of X-ray detector, which is, they can get very expensive if they're very big. And this instrument sort of runs for a couple of hours. It keeps spinning around the crystal, so it tries to see how it diffracts in 3 dimensions. Very powerful technique. But of all the techniques, NMR is the one that we tend to use most, and you'll see why. Just a bit slow. Of course, the solution very often is, you may say, well, what about if some of you work in materials chemistry, that you are never ever going to grow a single crystal? And sometimes what you want to do is get composite powders that you pack, and you can do powder diffraction in exactly the same way. You take your powder, you compact it in a little disc, and then you hit it with an X-ray, and you get a very sort of defined pattern of diffraction, which the solid state chemists use to try and determine how far the molecules are from each other in your powder. So again, versatility, ingenuity, a clever understanding of the theory, and also trying to do something clever with the data that comes out the other end. That's what this is about. Now, even though we think about data, and here's an example of a protein structure that's solved from a single crystal. And, look, protein structures are really quite remarkable things because they're not symmetrical, right? They're just really complex. And again, you'll see in the PDF, or if you go look up any crystal structure, and they appear in all sorts of papers, in journals, in textbooks. A structure like this early on did take, as I said, someone like Dorothy Hodgkin, the better part of a year or two to try and solve. Now you can do this in a week. You acquire the data very quickly, and you've got very clever computers and very clever algorithms which solve the structure for you. Now, the question is whether machine learning and AI can do it even faster. Because the problem with this is when you start off, you're starting from nothing. You just don't know what you've made. You're getting this data coming out and you're thinking, oh, I wonder if it does what I wanted to do. With AI, what you expect to do very early on is to see what similar data from other structures would have done and try and predict and cut the steps. So some people are arguing whether for complex biological systems, if you can crack a crystal structure now in a matter of hours or minutes, think how important it is for high throughput work. There's a company that was started by a colleague in Cambridge called Aztecs, where all they did is they made libraries of proteins with different molecules. Sorted, thank you. They make libraries of proteins with different molecules, and they have robots that used to do this. They take a protein, dip it into a drug, the drug would bind to a protein, they'd go to the X-ray diffractometer, they'd run the spectrum, they'd run the image, they'd solve it, they'd sell it to industry. Industry would look at what molecule, how it works with the protein, then they would go develop new molecules, new innovations, very, very clever stuff. For sort of practical science, there's also something very useful. I'm not sure if the graphic is going to work, which is why I did them side by side. So these are these molecules that are called catenanes. So they are effectively interlocked molecules. They're rings. They're like this. Right? They move inside one another. You can characterize these very nicely by NMR. But for a long time, people could not confirm, even though the NMR told you could make these catenanes, an innovation that won 3 scientists a Nobel Prize recently. Until you got the X-ray structure, you couldn't prove it unequivocally. And here is the interlocking ring. And here, I can't get the video. Ambition, if you're upstairs, if you touch the screen, the video will work if you just touch it where the video appears there. And you may just see it spinning around. And that's a very nice representation. Again, when the X-ray structure for these catenanes was first developed, it really created a boom industry amongst academic researchers for making these new molecules because, of course, they acted in effect as molecular switches. You could take the molecules and by making them rotate inside each other, you make something that's a switch. Wonderful work that's being done by someone who's at Manchester, David Lee, who's used this work that people like Fraser Stoddart, Jean-Marie Lane had done. Really, really beautiful science. In terms of X-ray data, the library for all X-ray data on the planet is the Cambridge Crystallographic Data Center, the CCDC. And it's a building right next to ours. And I have a colleague who works, and I said, look, I'm going to Africa. I'd like to do something really clever. And he said, don't worry about it. Show your colleagues this link. And it's got the little QR code and a link at the bottom. It's on the PDF that you'll all have access to. And what I didn't realize is that there is a program now called FAIR where you can download a lot of very, very clever software and tools to analyze X-ray data for nothing. They're available, and actually it's a resource that's set up, and a lot of people, they said they've been using, especially in Africa. It's a free resource. Look into this if you're interested in doing this. It's also not just about packages for solving things, but just tools for understanding crystal structures. And here it is, it's got the various loops, various links, it's there. I'd had no idea that's available because, again, a lot of these companies, a lot of these centers make money by selling services. Thankfully, they charge industry a lot of money so that we as academics pay little. It works out some of this you can get for free. So please look into this resource. Okay, so I think formally, I think I was told that we've got till 1:30 to have lunch. So again, I hope I'm not testing your patience, and I'm sorry for that, but we've lost a couple of sessions, and we're here to bombard you with information. So at the end of the day, even if you forget a detail, you remember a slide that you think that you will remember for your research was important. Go to the PDF, find it, and it'll give you what you want. Now, what I'll do is, let me go with NMR, and I'll try and do this in half an hour so you can then go off and sort of have the break before we come back again. Now, NMR is important. So I'm going to try to go through this relatively fast and focus on 1 or 2 slides where I want to talk about multiplicity. How many of you are aware of NMR as a technique? For how many of you is NMR completely new? Many of you have not put your hand up for either. So have you covered NMR as a course? Who's seen NMR in a course or covered it at all? Okay, so not very many. Okay, so let me show you why NMR is very useful and typical pictures of what the NMRs tell you. NMR is relatively expensive. It's a robust technique, and once you learn what to do on one instrument, you can learn and you can get any NMR spectrometer in the world and do an experiment. It's very interchangeable. It helps identify unique environments. Remember the benzene problem a moment ago. And all have the same theory. What you're doing, the experiment is this. You hit your molecules with radio frequency pulse. I'm going to take my benzene again. We're going to concentrate on the black balls, which are the carbons. You hit this with a radio frequency pulse, and all the black spheres are going to get excited in exactly the same way, and as they relax to equilibrium, they're going to give off exactly the same signal. That's NMR. Excite, relax. Excite, relax. But because all the carbons are the same, they all excite exactly the same way and relax exactly the same way. So what we're detecting, for those of you who are mathematical, is we're doing an intensity versus time map. And this free induction decay, very aptly, is what would happen if you strike a bell. It's loud at the beginning, and it dies off as a function of time. So the FID is a bit like the bong effect. And that's what you detect every time. That's what we record. To a chemist, that's a meaningless, pointless way to record data. So we rely on our mathematician colleagues again, and what you do is you take this intensity versus time trace, and you do a Fourier transform, which is a clever mathematical tool, and you turn this into a frequency intensity scale. So this FID gives a sharp line, which I'm sorry at the back you may not see very well. It gives a single signal, and that is the NMR spectrum. Now, let's look at some examples, keeping an eye on the time. Here's benzene, planar, aromatic. All carbons are exactly the same. 6 black dots, but they're all identical. So they will give exactly the same signal. So we may as well say, as they're all the same, there is only one environment, and it gives one signal in the carbon spectrum. And it looks like this. It goes bang, a single line, and nothing elsewhere. The symmetry says it's one line. The x-axis tells us something very useful. That line comes at about 130 ppm. That's the x-axis reading. 130. That's a high number. What experience tells us is a high number for a carbon means that carbon is most probably part of a benzene. It's an aromatic. It's a highly conjugated system. That's information that one line tells us. Of course, benzene is also made up of the white hydrogens. There's 6 of those. If we excite, relax, they do it in exactly the same way. So all the hydrogens are identical. So it's like having one hydrogen. And you run the proton spectrum, and not surprisingly, it has one line, one single sharp line. And on the x-axis, it comes at just above 7 ppm. Don't worry about the scales, right? That's not important for us now. But it's 7. It's not 2, it's not 5, it's not 1. It's 7. That says it's aromatic. It's part of the benzene ring. And there is a solution to our problem. Cyclohexane looks like benzene, 6 black dots with white hydrogens connected, but this is not aromatic. If you've done molecular orbitals or you've done chemistry, we talk about aromaticity, this is an alkane, not an aromatic system. So what do we expect to see in the carbon spectrum? Well, they're all exactly the same. So what would we expect if they're all the same? One signal. What do we see in the carbon spectrum? One signal. You say, but how's that different to benzene? The benzene one came up at 130 ppm, which is diagnostic for aromatics. This one comes down at about 25, 27. That's diagnostic for cyclic alkanes. It's different molecule, symmetry gives the same line, but it's a different spectrum, okay? Of course, cyclohexane can do very clever things because it flips between its chair and its boat form, but as far as the NMR spectrum is concerned, it doesn't care. What about the protons? What about the hydrogens? Well, there are 6 of those, but they're more or less the same, so you shouldn't expect the spectrum to be complicated. What do we see? One peak, they're all the same. Look at the x-axis, 1.5 ppm, not 7 ppm. 7 ppm in a proton spectrum means it's aromatic. 1.5, 2 means it's an alkane. The x-axis and the symmetry tells us it's cyclohexane. Right, got it? Now we're going to go through other molecules and follow exactly the same logic. So here's cyclohexane, it just can flip between various forms. Take cyclohexane and make one of the bonds a double bond, cyclohexene. Look at that molecule just for a moment. Is the molecule symmetrical? No, now it's different. It has a plane of symmetry that runs through the molecule here, which means there are only 3 unique carbon environments. This one is the same as this one, that one is the same as that one is the same as that one. So we should see 3 signals. You run the carbon spectrum, thank goodness you see 3 signals. 1, 2, 3. The x-axis, what's the x-axis tell us? This one is standing off on its own at about 130 ppm. We said, you said around 20 is alkane-like. What comes up at about 120? Double bond carbons come up at around 100. Great. That carbon must be that one. These 2 are alkane-like. That's those 2, so they come down in the alkane region. Break the symmetry, more signals, and their position tells you what type of carbons are. What about hydrogens? Look at the hydrogens. We have an alkene hydrogen and 2 sets of alkane hydrogens. The molecule's not symmetrical. We see fundamentally 3 different environments. That one, those, and those. What do we see in the proton spectrum? 3 environments. One at around 5.5 ppm. That's where alkene hydrogens come. That's this one, is that one right there. And these 2 are that and that. Benzene was a single, cyclohexane was a single. You break the symmetry, you get this. Now you can see why we use NMR almost always. Very clear data. We can keep playing this game over and over again. Now I'm going to desymmetrize. I'm going to break the symmetry of cyclohexane by putting a methyl group at that position. The molecule has 7 carbons. Does the molecule have any symmetry? No. If it has no symmetry, all carbons must give their own signal. So if we look at the carbon spectrum, what do we count? 1, 2, 3, 4, 5, 6, 7. Perfect. We predicted 7 lines, we see 7 lines. X-axis. These 2 seems to stand on their own. These 2 come at around 130 ppm. That's where alkene carbons come, which means those 2 are 1, 2. Now, which one of the 2 it is, I may not know. We may need to do some other experiment, but those 2 alkene carbons are those. 1, 2, 3, 4, 5 are 1, 2, 3, 4, 5. They're in the alkane region of the spectrum. Can you see how the pattern builds up? This is not hard. As a matter of fact, it's sort of a trick I tell undergraduates once they learn to go home and do over the Christmas vacation with their family and friends over dinner. It's a thinking person's puzzle. Once you can draw a molecule and you know the symmetry argument, you can predict the number of carbons. Here's the proton spectrum of this. Of course, we have 1, 2, 3, 4, 5, 6 proton environments. We see 1, 2, 3, 4, 5, 6 proton environments. Now, this is starting to get messy, by the way. You'll say, hang on, these spectra have got lots of lines. This is now called coupling, because hydrogen environments that are not symmetrical can see each other, and there is this thing called multiplicity. Little complicated, Takes us about 2 or 3 lectures to teach in Cambridge. Just be aware, if you're interested, you can go read about it on Google, right? It's there. I will pick 1 or 2 examples where I'll show you in a simple way how the multiplicity tells us about neighbors. In other words, how many lines means what. Now, we were interested in what happens with the x-axis, and there are these tables of data which says in the carbon spectrum, depending where the carbon is in what functional group, is there are particular areas where you'd expect it to come. So for example, things that are part of ketones, aromatics, all the way down to alkanes, they come at very specific part of the x-axis. Remember, aromatic carbons come at about 130 ppm. Aliphatic carbons come down at about 20. It's a difference between being up here or being down there. And you can do the same with proton spectrum. The proton spectrum is typically between 0 and 10 ppm. I always tell people in the lab, acquire a wider spectrum just in case there are stray peaks because of some property of the molecule. But typically a proton is in the region of 0 to 10 ppm. Aliphatic and aldehyde protons come all the way up here, alkenes all the way down to alkanes. Diagnostic information. So here is something where we'll try and look at the splitting pattern a little bit in a little bit more detail, and that'll it must be finished just in time. So here is an alkane with an iodine on one end, ethyl iodide. So what we've got here is CH3 next to CH2 next to an iodine. How many carbon environments are there? The molecule is not symmetrical, so we expect 2 carbon environments. 1 carbon environment for this one and a carbon environment for this one. Are they going to come close to each other? One will be slightly higher, more to the left than the other, because it's next to an iodine. So this carbon is next to an iodine. Iodine's electronegative. Iodine draws electrons towards itself. So the carbon next to it has electron density withdrawn. Therefore, it becomes de-shielded. Therefore, it appears more to the left. That's the rule. You may not remember that. I won't remember that in half an hour. It doesn't matter. What you need to remember is that groups next to carbon affect them enough that they can push them either to the left or the right of the spectrum. And what we see in the carbon spectrum, it doesn't come up very clearly at all. I'm sorry about that. There are 2 carbons here and here. They're 2 sharp lines. One that's next to the iodine is further to the left than the one that's a methyl, which appears further in that direction. In these carbon spectra, every unique carbon environment appears as a sharp line the way that they're acquired. Now what we have here is the carbon spectrum, and there's something above it called a depth experiment. And again, you'll see this clearer in the slides. A depth experiment is a clever experiment because it says to the spectrometer, talk to the molecule, and carbons that have an odd number of hydrogens attached, CH3 or CH1, make them appear in one direction, point up, and make the even carbons, that's CH2s, and C with no hydrogen, appear in the other direction. As a matter of fact, quaternary carbons don't appear at all. So if you look at this carbon, that's a CH2. That carbon has 2 protons attached, therefore it's an even carbon. The carbon next to it here is a CH3. That has 3 hydrogens, that's an odd carbon. So they should appear opposite to each other. And what you see when you look at the spectrum, 2 single lines in the carbon in the depth, one is pointing down and one is pointing up. And that gives you the useful information about whether something is odd or even. Again, keep in mind, nothing more that when you look at the carbon spectrum, you can run other variants of the carbon spectrum, because if you've got lots of lines, I mean, some of the spectra that you'll see on the slide rack that you have that we may not be able to cover today anyway, something like cyclosporin or cholesterol, 30 carbons I think cholesterol has. That's a lot of carbons. How do you know the difference between one which is a CH3 carbon as opposed to one which is CH2 or one which is CH1? They're just all next to each other. You run this very clever experiment called a depth experiment, and the CH3s and the CH2s appear opposite. So they betray which one is which. Very powerful technique. Now, these can be run relatively quickly, right? As the modern spectrometers, if you've got a reasonable amount of sample, you know, if it's an organic molecule, about 5 milligrams, 3 milligrams. A carbon experiment is run in about 20 minutes. If you want a good one, maybe 2 hours. Pulse, listen. Pulse, listen. Excite, listen. Excite, listen. And if you do that over and over again and keep adding it together, your signals get stronger and the noise disappears. So carbons take long, and there's a reason. Carbon-13 is not abundant, it's 1%. We run carbons longer. But if you do clever things to the carbon spectrum, you get the difference between a conventional carbon and a depth, and that betrays information about the carbon. Hydrogen, proton NMR, right, that's the most abundant hydrogen, you run that in 2 minutes. You can run a proton spectrum in 30 seconds if you wanted to. It just won't look very pretty. It'll have a lot of noise in it. So you'd look at this and say, okay, all right, we know NMR now. Even those of you not done NMR, and at the end of the session, maybe I'll randomly go around, give you a molecule and get you to predict what the structure should look like. It's okay, now we know about this. Even if I've not done NMR before, I can work this one out. Has no symmetry, so it had 2 carbons, one will be at a different chemical shift to the other. We agree. What would the proton look like? And you'd say, okay, same rules. But there are 2 different types of protons. The 2 protons that are here on this carbon and the 3 protons that are on this one. So we should see 2 different environments. That's exactly what you see in the proton spectrum. There they are, 1, 2. Can you tell the difference between that one and that one? You can. You can tell 2 ways. First way is that there are 3 hydrogens on that carbon, 3, and there are only 2 hydrogens on that carbon, 2. So if you look at the relative height of your 2 peaks, one will be taller than the other because there are more hydrogens ascribed to that. So this one is the taller of the peaks, and it's further from the iodine. So those hydrogens appear here at just below 2 ppm. That CH2, because it's next to the iodine, is the one that's further up, and this is shorter than this one because the taller one is the CH3, that's 3 hydrogens, which is furthest from the iodine. That's how the rule plays, right? You're just thinking about number can tell you height, where they are on the molecule tells you the X position. Now about coupling in the 5 minutes that are left. This takes a little bit of thought, so just follow this. In a hydrogen, because this is a property that we see specifically in hydrogen, also in carbons, but often we don't worry about this, there's something called coupling. So the relative position on the x-axis tells us something about where they are on the molecule. That is next to an iodine, so that carbon and that hydrogen are further to the left. But you think, I'm not quite convinced. Because on the x-axis, whether it's here or whether it's here, I'm not convinced. What other information have you got? And this is where coupling constants are unequivocal. And this is how coupling constant works. For hydrogen, there's something called the 2ni+1 rule, but all you need to do is just follow this. If you're looking at these hydrogens, if we are right, and if these protons are represented by that resonance, it's not going to appear as a single line. Because those hydrogens look at the molecule around them and they see, look around, this is just hydrogen. Imagine you look at the world through hydrogen glasses. This hydrogen looks around the molecule, looks one side and says, iodine, you don't matter to me. Don't see you. Then looks at the other side and says, oh, hydrogens on the next carbon. You're my friends, I see you. Therefore, in the NMR spectrum, I must declare a way that I see that you're there. So those 2 hydrogens look next door and they say, hi, hydrogens. And the hydrogens look back and say, hi. And the CH2 says, how many of you are there? And they say, there are 3 of us. And according to the 2ni+1 rule, these hydrogens, which have obviously done very well in their chemistry degree, know the rules, and the rule is you count the number of hydrogens next to you and you add 1. So it says, hello, there's 3 of you. If there's 3 of you, then I am going to appear as a quartet, a 4-line multiple. 1 to 3 to 3 to 1. And that's what this looks like, but we cannot see this very clearly at all. So that appears as a quartet, a 4-line peak because of its neighbors. That is indisputable. Now there is no doubt that the proton resonance we suspected was this one because it's next to the iodine. Because these protons appear as a quartet, according to the count the number of neighbors plus 1 rule, so then that one has to be a quartet. That is a quartet, therefore our assignment is unequivocal. Of course, by the same rule, you say, okay, so what happens to the other hydrogens? Those hydrogens we suspected were these ones here. They're more to the right because they're further from the iodine. That's pretty fair. But if this one says to the hydrogens, hi hydrogens, how many of you are there? And they shout back, there's 2 of us. Then this one says, oh, if there's 2 of you, I must appear as a 2 plus 1 multiple. It appears a triplet. 1, 2 to 1. And that's exactly what this is right here. It's a triplet. And now we've analyzed and characterized this molecule beyond dispute. Now this would take about 4 lectures in an undergraduate course in Cambridge. I've just done this in about 11 minutes. But you can get it. You don't have to understand the underlying theory. I need to draw quantum mechanics split and pattern. But it's a simple rule. Look at the molecule and follow these simple rules. Okay? What I was going to do a little bit later is try to work through some problems. We may not get time to do that because I think it's more important to tell you about their techniques. So that, for example, now by NMR, even if you've not seen it, you'll think, if I see an NMR spectrum, in a proton, there are all these things called multiplets. It's because this how many neighbors plus 1 rule applies. But then again, you can do fancy things. Right? That's 1D. You know, sometimes you can't do it with just a standard spectrum where you've got ppm versus intensity. You do clever things like 2D spectra. You now do the experiment in 2 dimensions, and you get a pattern that looks like this. And this is, again, is carbon, so you can see the pattern a little bit more easily. And the COSY tells us which protons are next to which protons next to which protons. Now, of course, this molecule is so easy, you could have solved this without doing any of this fancy 2D. Once you know the rule that we talked about, you'll be able to characterize it on your own. But the 2Ds really help you crack the problem. And if you said, okay, once I know what protons are next to 1 protons, can I work? Is there any clever way where I can confirm to which carbon a particular proton belongs? And you do this with these carbon-proton correlation experiments. Well, I can look at the proton spectrum at the top, say that that methyl group has a carbon at about 15 ppm, that one is coupled to a carbon at about 25 ppm, and so on. So 2D is a whole different subject, which we do in 3rd and 4th year of our undergraduate course. It's a little bit more specialized. But since the scientists were transferring information, NMR has 2 and 3 dimensional versions, and the 2-dimensional versions are very, very useful indeed. So even if you just look at this one at the top, let's play the same rule, and I think this is the final slide anyway. This is just to show you what cholesterol and cyclosporin look like. These are very complicated molecules. So if you look at the spectrum a moment ago, just do exactly what we said. If you look at the carbon spectrum, how many carbon peaks would you expect? If you look at this molecule, there are 1, 2, 3, 4 carbons. Where would you expect them to come? The carbon that's next to the iodine would come furthest on the left, then the next one, then the next one, then the next one. How many proton environments would you expect in the proton spectrum? 1, 2, 3, 4. How many do we see in the proton spectrum? 1, 2, 3, 4. The one that's next to the iodine is furthest up to the left. But if we play this multiplicity rule, how many proton neighbors does this environment have? 2. So what is it going to appear as? A 2 plus 1 equals 3. So go to the other end, look at this one. This is going to be the tallest of the 4 peaks because it's represented by 3. But if you look at the CH3, how many neighbors does it have? 2. What will it appear as? Triplet. 1 to 2 to 1. Triplet. Look at this one. Now it gets a little bit harder. How many neighbors does it have? 3, 5. So it's got 3 from here and 2 from here. So we'd say, okay, it'll be a quartet due to this and a doublet due to this. So essentially going to be a doublet of quartets. So essentially going to be an 8-line multiplet. You've got to treat these both separately. So that one will be a quartet, a 4-line multiplet of triplets. Oh, sorry, it's a triplet of quartets. So it's 4 plus 4 plus 8, it's 12-line multiplet. And that's what it is here. It's a complicated 12-line multiplet. What about this one? This is 2 due to this neighbor, 2 due to this neighbor. Remember, these ones can see protons on either side. It's a triplet of triplets. It's going to be 9 lines. So the multiplicity tells you everything you want about the molecule. Now, that's as hard as it gets. So that's your crash course in NMR. If you give you more complicated molecules, like cyclosporin or cholesterol, but all it does is it just makes it a little bit more challenging. The theory is exactly the same. Count the number of carbons, see if there's symmetry, count the number of hydrogens, see if there's any coupling due to the neighbors next to them, and that's it. Okay? So that's a crash course in NMR. And NMR is a very powerful technique. This is the one that I suspect that most of you who make a valuable molecule will send it somewhere else for someone else to run the NMR spectrum and then send you a printout. This matters. This stuff is important. And if you want to know how to process the data, Topspin, Mestranova, their online modules, and then we'll pick up later. There's some more presentations after.
Wow, that was it was a master class. Thank you, Dr. Nick. Thank you so much for breaking it down and making. If they taught me chemistry like this, I for like chemistry past the way I like them. Yeah. Thank you, sir. Thank you so much. So we'll go for our lunch now. Okay, you remain seated. They'll bring the lunch to you. We have 1 hour till 2:30. We have 1:30 to 2:30 for lunch. So please remain seated. They'll bring your lunch to you. You can have your lunch, rest a while, and by 2:30 we'll reconvene. Thank you.